Hello students, this is some instruction of how to actually determine the rate law, come up with the equation. Let's dig in. We obtain the rate law from experimental data. Here's our reaction. We are trying to find out what the order of the N2O5 is. So we'll just continue to call that N. Now, just a reminder, we know if we were to graph time and concentration of reactant, that it's not a linear relationship. It is an inverse curve because rate changes as the reaction proceeds because the concentration of reactant is decreasing. And the concentration of reactant plays a huge role on the rate of the reaction because we get less and less and less to come into contact to form product. All right. Well, this shows a graphic representation of this. So as the reaction proceeds, we're measuring concentration. But the method of initial rates, what it does is changes the concentration of the reactant and measures initially what the rate of reaction is. And so when the concentration is 0.9 molar, the initial rate is exactly this. And then when it's 0.45, it's this. Now it seems like what was done was the slope of the tangent, so we got the instantaneous rate, but that's the idea. Now what you can do is just really look at how concentration is changing and then the impact on the rate. So in essence, what we could do is say, well, we are doubling from this to this trial, we are doubling the concentration. All right, well, what is happening to our rate? Forgive me, in the opposite direction. We're halving it there. We're doubling concentration from 0.45 to 0.9. Well, what happens to rate? Oh, it also doubles. So we would anticipate then the order is 1. But let's prove it. So if you're ever asked to show work, well, we're trying to come up with the rate law. Well, let's call this 1 and 2. So the rate of 1 will be the rate constant 1, the concentration of N2O5 1, and we know to some order, and we're trying to find that. And we have another trial, so the rate of 2 will equal rate constant. It's the same reaction. It's happening at the same temperature. So actually, these K's are the same. So I'm going to write K1. But we know that this is the second concentration at that trial times some exponent. Well, why don't we set up these fractionally to each other? So the rate of 1 is 5.4 times 10 to the minus 4th mole per liter second. And that equals K1, and the concentration in this trial is 0.90. We're trying to find that. Over 2.7 times 10 to the minus 4th mole per liter second, 0.45 molar. Now, same reaction, same temperature, so therefore these are the same. They're going to cancel. So do we see? What we can do is divide this, and of course that will be 2. 0.9 divided by 0.45 is 2. To some exponent, 2 to what power is 2? And equals 1. So mathematically we proved that then N2O5 is a first order reactant. There's our rate law. Okay, let's do a little bit more intense. So what if we started with this data? All right, and here we have 2 reactants. So we are trying to come up with the rate law. Let's imagine for this reaction, we were asked to come up with the rate law for the reaction. If we were asked to come up with the overall reaction order and the value of the rate constant. All right, the rate law. Well, I know generically it is going to be NH4 plus to some power, and then NO2 minus to some power, and let's just call it M. All right, if I look from experiment 1 to experiment 2, I have kept the concentration of ammonium the same. So if there's any change to rate, it's not because of the ammonium. From 1 to 2, ammonium is not changed. But I have doubled nitrite. When I double nitrite, look at that. The initial rate doubles. So if I double this and rate doubles, then that means that M is first order. Or M is 1 and then nitrite is first order. Now of course, a 1 is understood to be there, but just as we're initially starting this, I'll put the 1. All right, so next, if we go from experiment 2 to experiment 3, my nitrite is the same. So if there's any change on the rate, it's not because of this. We double ammonium. If we double ammonium, oh, look at that, rate doubles. So that means that N is also 1, or ammonium is first order. So we came up with the rate law. Okay, next, really easy. The overall reaction order is simply a result of adding the individual reactant orders. So, first order and first order, 1 plus 1, 2. So the overall reaction order is 2. This doesn't really mean anything, it's just something else you could be asked. If this were second order and first order, then 2 plus 1, the overall reaction order would be 3. All right, third, the value of K. Choose one line of data. You've come up with the rate law. You're simply going to input the line of data and then solve for K. So, rate over ammonium to the first, nitrite to the first, we equal the K. I'm going to choose either the final or the first line. If I choose middle, my eye's going to read different sets of data. So I'll go ahead and just input the first. So my rate there is 1.35 times 10 to the minus 7th mole per liter second. And ammonium is 0.1 mole per liter and 0.005 mole per liter. Be careful of units. Do we see our unit will end up being liter per mole second, and numerically 2.7 times 10 to the minus 4th. So there's the 3 things that we were asked.